Okay, so this is a second video covering mechanics with somehow a little bit more challenging problems. I have like 10 problems for you, and then I think it will be it. So this one, you can pause the video and try to do it. Because even though you didn't take, most of you didn't take calculus, you might be able to do it. So a particle starts from rest, so initial velocity is 0, and you have the acceleration. So usually we always deal with problems with a constant acceleration. So it means that if you look at the acceleration as a function of time, you see that the acceleration stays the same. Okay, so you start at 0 here, you have some acceleration, and the acceleration is constant because the force is constant. Now, if you were to find this area here, you see you have A, which is the acceleration A times T. That's going to be the area, okay, under the acceleration as a function of time. And that will also give you delta V, right? So delta V for constant acceleration is just A, the acceleration times the time elapsed, or the final velocity equals initial plus AT. Conclusion, the delta V, the change in velocity during the time elapsed, is the area under the function acceleration as a function of time. So here they give you the acceleration here as a function of time. You see it's not constant, okay? It's a linear equation, 2t. So it's going to be something like this. Okay, so 2t, the slope is 2. So if we want, and we have the time elapsed, so the time elapsed is 3 seconds. So after 3 seconds, the acceleration will be 6, but it keeps increasing. So the change in velocity that will happen is just this area here. So the area will be delta V. Okay, so it will be the area of a triangle, which is 1/2. The base is 3. And the height is 6. 2 times 3 is 6. Okay, this is 6 meters per second per second. So that will be 6 here. So that will be 9 meters per second. So the increase in velocity will be 9 meters per second. So the final velocity equals initial plus that means plus 9. Okay, that will be your delta V. So, and this is 0. So the answer is B. Okay, so the next one is easier. What's going to happen if you have a resistance? So first of all, when you have so one thing to know is that when you have a projectile motion, if there is no air resistance, the only force acting will be the weight. Okay, and so that will be X and Y. So if you launch here at 40 degrees, okay, that will be the largest range that you can get. Okay, so that will be called the range. Now, if you shoot at 60, for example, it's going to be the same as if you shoot at 20, because they add up to 90 degrees. So anyway, that will be 45 degrees. And you always have the weight pulling down. Now, if you have a resistance, that means you're gonna have, if you are just looking on the x-axis here, so along the x-axis, the projectile has a horizontal velocity, which does not stay constant in that case because you're gonna have drag. And the drag will oppose the motion. So if it wants to move this way, you're gonna have a x component of the air resistance that will oppose the motion. So obviously the range, if you have a resistance, it's gonna decrease. It cannot go as high, as far. So on the way up, you're gonna have the drag that will be down and the weight that will be down. So it's not going to go as high. And then on the way up, you're going to have the weight down and the drag will be up. So it might reach, if it has enough time, it will reach terminal speed. So here it's not going to go as high. And if it reach terminal speed, then it's gonna go straight. It could even go straight down, right? So it will be more steep here. So anyway, the answer is decrease. So let's look at number 3. So this is just rotational dynamics. So it's a typical question. So when something wants to rotate about an axis of rotation, so this picture comes from the textbook Conceptual Physics by Paul Hewitt. I use a lot his material. So anyway, if you try to rotate, so rotate this way, how easy it's gonna be depends on the distribution of masses about the axis of rotation. So closer the mass is from the axis of rotation, less inertia, less resistance to the twist that you are trying to apply. So you are applying a torque, okay? Because you apply a torque, there will be an acceleration, rotational acceleration, but it depends on the inertia. So if the masses are far away from the axis of rotation, inertia will be larger. Okay, so if you compare a solid sphere and you try to spin it, and you apply the same torque to a hollow sphere, let's say they all have the same mass, you see that the smallest inertia will be for the solid sphere because more mass will be close to the axis of rotation. So that will be 2/5, which is 0.4. This one is 0.5, so that will be the second one. It's close because you have still mass close to axis of rotation. This is 0.6 because it's hollow, and this is the worst here. So if you have a race on an inclined plane like this, the first one to reach the bottom will be the solid sphere. And that will be true regardless of the mass, because going down the inclined plane, the only force acting is gravity. And so it's like they are in free fall, right? So the mass doesn't matter. The size actually does not matter. What matters is the inertia here. So between, for example, a solid sphere and a solid cylinder, the sphere will arrive first, right? You have many videos that will explain that. So if they have a race, regardless of the mass, regardless of the size, it will be the solid sphere that will arrive first because of inertia. Solid sphere, hollow sphere. Here is going to be 0.4 and here is going to be 0.666. So this one has more inertia. This one will arrive first. Okay. So average power output. So this one, you should pause the video. It's not a hard one. So going up a staircase, you have a mass here, and you are doing work against gravity, right? So that will be the height, and the work done against gravity. You are doing work. The work that you are doing, okay, against gravity is just the change in potential energy, which is mgh. Okay, because you have to lift your own weight, or you can think of that as work is the force here times the displacement. Displacement goes from point A here to point B, and the work done against gravity doesn't matter what happens in between, it's just initial position and the final position. Now, the definition for the average power is the work done over the time elapsed. Okay, so in that case, it will be the mass, which is 60 times g times the height, 10 over the time elapsed. So 2, and so that's going to be equals to 600 divided by 2, which is 300 watts. Okay, so it's joules per second. This is joules here. So 300 watt, which is nothing. Okay, so let's do the next one. So here you have to remember spring oscillations. So when you have an oscillation and there is no friction, the energy involved will be elastic potential energy, and an elastic potential energy is 1/2 kx squared. That will be when the spring is compressed or stretched, and then you have kinetic energy. So this is actually it's a simple harmonic motion. So it's easy as long as you know the definition. I mean, you know what's going on. So you have a spring here, you have a mass, you can stretch. So this is 0, you can stretch it here up to x. So the potential energy will be 1/2 kx squared. Energy, so the mechanical energy is 1/2 kx squared here. And then all that potential energy is going to turn into kinetic energy, and then back to potential energy, and then back to kinetic, and then to potential energy. So all that potential energy that you begin with will be equals to the kinetic energy when it goes through the equilibrium, because when it's at the equilibrium, there is no, when x equals 0, this is x is maximum. Okay, because there is no stretch. So I forgot the question. The maximum kinetic energy of the mass is equals to, so it will be at the equilibrium, it will be 1/2 kx squared because of conservation of energy. Okay. So this one, you have two ways to do it. You can guess, given the given the given the numbers here, given the multiple choices, you can use the answer. So you can pause the video and try to do it. So here, the important thing is says that it's an elastic collision. So elastic collision means it's gonna bounce, hit and bounce. And it also means that the kinetic energy is conserved. So it means momentum is always conserved if it happens quickly and we neglect the external force. So usually momentum is always conserved. Kinetic energy is conserved only when it's elastic and it doesn't stick, for example. So you always have M1 V1, conservation of momentum, and then V1 prime plus M2 V2 prime. So it's two things colliding. This is the number one, system number one, system number two. That will be the speed before, and that's the speed after. The prime is the speed after. And if kinetic energy is conserved, it means that the total kinetic energy before, so N1 M1 square plus 1/2 mv2 squared equals kinetic energy after prime plus 1/2 mv2 prime square. And I forgot this one is m1, m2, m1, m2. If you play with those, you get your first equation. Second equation is a headache, but if you play with those two equations, you find, and that's the one that you have to remember, because you have equations, right? But it's very hard to memorize. But the one you can memorize is that by playing with these two equations, we're going to find that the relative speed, the relative velocity, relative velocities are the same with a minus. So it means that V1 minus V2, so these are the relative velocity, should be equals to minus V1 prime minus V2 prime. So the relative velocities stay the same in magnitude. So anyway, let's see what's going on. You have 2 kilograms. So this is 2 kilograms. That's my number one. And it has a velocity of 3 meters per second. And this one is not moving. 4 kilograms. It's not moving. So what can happen is that this one might be bouncing off. And this one might be moving a little bit. Could be this, right? Because this one is bigger than that one. Could be this scenario. So what do we have? Momentum before, it's going to be 2 times 3 equals momentum after. So 2v1 prime plus, so that's going to be after. So 4 times v2 prime. So here, momentum before of this one is 0. So I have this equation here, which is the same as that one. And then I know also that the relative speed here, so v1 minus v2 is just 3. So you have 3, so 3 minus and v1 prime minus v2 prime. So it means when I'm looking at the velocity, relative velocity after, you should get minus 3. Right? So, and we don't know that velocity. So you can play with those equations and solve, or you can look. So let's check the answer. So this answer doesn't make sense because that will mean that mass here does not lose any momentum, but some of the momentum has been transferred to this one. But you can check with the equation, but this one doesn't make sense. Number 2, we're gonna have, let's try 1. So number 2, we have 6 equals 2 times 2 is 4 plus 4 times v2 prime. So let's see, 6 equals 2 times 2 is 4, okay? So that would means that 2 equals 4 times v2 prime. So in that case, v2 prime has to be equals to 1/2, okay? And if you do the relative speed minus v2 prime, you see it's not going to work. Let's see if it's working or not. So we have v1 prime, which is 2 minus v2 prime 1/2, and that's not going to work, right? Because we want to have 3. So this one, that doesn't work. This one doesn't work. So let's check B. So if we look for B, we're gonna have 6 equals 2 plus, so we have a 2 here, okay, plus 4 times v2 prime, which is that v2 prime equals 1. Okay, so let's check with equation 2. So we have minus v1 prime is 1 minus v2 prime is 1, which is 0. So no, that doesn't work. Now you could have guessed that it's going to be number A, because this one is big relative to this one, so it has to bounce off. And the only negative equation is A. So I think that's what they want you to realize, right? So in that case, you're going to have 6 equals 2 times minus 1 plus 4 times v2 prime. So in that case, v2 prime will be 8, 2, right? Because it's going to be 8 divided by 4, so it's going to be 2. So let's see if this one is okay. So minus v1 prime is minus 1 minus 2, which is 3. So check. So the answer is A. So the next one, you are not supposed to know. You don't have to memorize the angular inertia or the moment of inertia, right? So it will be given to you. So in this one, it's not given to you, but you're not supposed to memorize them. So if you have an axis of rotation here, maybe you have a rod here, and the rod has a mass m. So if you apply a force here at that distance there, so the force is applying a torque, right? And the definition of torque is just the force times the distance to the axis of rotation, so to the distance. It's actually the perpendicular distance, but here the force is perpendicular, so I don't have to worry about it. So if there is a torque, there will be a twist, and you're going to get an acceleration. But how much acceleration depends on the moment of inertia. So the torque is, the acceleration will be proportional to the torque, but inversely proportional to the moment of inertia. Right? And what do they want? They want the acceleration. Okay, so that means the acceleration will be the torque, which is the force. Okay, so it's 5 times the distance, it's 1 meter. So 5 times 1, it's applied at one end over the moment of inertia. And the moment of inertia for a rod, here it will rotate at one end, it's going to be 1/2, 1/3 the mass times the distance square. Yes. Okay, so it's going to be 1/3. The mass is 2. And the distance square is 1 square, which is 15 divided by 2. So the acceleration is 7.5 meter per second. No, sorry. It's not the right unit. It's going to be rad per second per second. So the answer is C. So this one is easy, and you don't need to know that. It will be... Okay, so this one, you don't need to know the equations, right? You just, it can make sense. So you can pause the video and try to solve it. It's a conceptual question. So it's about banked road, right? So if you have like a race, like you have in Daytona Beach, for example, you have a car here, and it's gonna go around a circle. So this is the center of the circle, so it's gonna go around like this. And in that case, there is a centripetal force here. You need to have a centripetal force. The centripetal force can be provided by the friction. Okay, so it wants to slide down, but there is static friction. But also mostly by the normal force. So it means you can still go around the circle even without friction. So here they talked about there is no friction, let's say. So you're going to have the weight here, and you have the normal force there. And you see that one component, so forces comes into components. So one of the components here, of the normal force will provide centripetal force, right? Because otherwise, let's say you are driving, you could go off tangent. So you need something to push the car toward the center. But it makes sense that if you increase the angle here, so then you might slide down. So it makes sense that for that not to happen, you have to go faster, right? It makes sense. Like if it goes like this, if at worst, if it's inclined so much, the car will slide down. So that means the answer is A. Now you can do the math. I'm not sure the math will be for an algebra-based class, or it will be more advanced. But if you do the math, you see that the required speed, okay, if there is no friction, it's going to be the radius r of the circle g, and then you have a sine. No, you have a tan alpha. Okay, so if alpha goes up, tan goes up, so the speed also has to go up. Okay, you can look on online how to solve to find out, but it's just conceptual here. Okay, let's see if we have one more. We have two more to go. So this one, we want to find, it's an inclined plane problem, and it will be easier if you use conservation of energy to solve it, right? So we can use conservation of energy here. So you have an inclined plane. This is 30 degrees. And just to see if you can also if you can figure out the math without a calculator. So that will be the height, okay? And you have the distance here, t, so you can find the height, and it's going to go down slope, but you have friction opposing the slide here, Fk, and of course you have the component of the weight here, making it going down slope, and you always memorize that component of the weight will make it go down. If they are equal to each other, they will go down at the same speed, and the kinetic friction is the kinetic the coefficient times the normal force. And you have to memorize that on the inclined plane, the normal force equals mg cosine. Okay, so each time you have an inclined plane, mg sine, it's the component of the weight that makes the object slide, and the normal force, okay, so it's like a reaction force, that normal force here, it's going to be mg cosine. Okay, and you have the weight. You have the weight down here, and you have one component of the weight here, which is mg cosine. Okay, so but so if this one is larger than that, it's gonna accelerate. If they are equal to each other, then it's gonna go at a constant speed. But that's so here they want you to find out what's gonna be the speed at the end here. Okay, so we're gonna use conservation of energy. So here the only energy it has is potential energy. So that potential energy is going to be turned into kinetic energy plus in magnitude the work done by friction, right? Or you can say potential energy minus the work done by friction, because friction is going to take away some energy, turn that into heat, will be what will be left at the end here. So at the end, you're going to have kinetic energy. At the beginning, you're going to have potential energy, and some of the potential energy is lost to heat because the work done by friction. And the work done by friction is just the force here, kinetic friction, times the distance. Okay? So once you understand that, I can remove it. And you can say that mgh, so that will be potential energy, equals the kinetic energy, so 1/2 mv squared, plus the work done by friction, which is the force of friction, so the coefficient times the normal force. So normal force is mg cosine. So I'm going to put mg cosine, and then don't forget to multiply by the distance. So you see the mass, we don't care about the mass, right? And then the height will be, so we need to find the height, and we have the height here, and we have that distance here, and this is 30 degrees. So the height will be sine 30 times the distance, right? So it's going to be sine 30 times the distance equals 1/2 v squared plus mu k g. So you have g. So cosine 30 is about square root of 3/2. So you need to know that it's about 0.87, and sine 30 is about 1/2, right? So here we have a cosine 30 times d. So this is 1/2 here. You can multiply by 2 everything, and this is about 0.9. Okay, so because we cannot have a calculator, so I'm going to try to simplify as much. So I multiply everything by 2. So we're going to have a g times d equals v squared plus multiply by 2 times the coefficient times 0.9 times g times d. Okay, so we have v squared. So d is 5 meters, right? So it's going to be, this is 5, and this is 10. So it's going to be 50 minus, we have a 2, we have a 0.4, we have a 0.9, we have a 10, and we have a 5. So that's going to be 36, right? So 0.36. That you multiply by 10. So that's going to be 5 times 2 is 10. So you multiply that by 100. So that means v squared will be equals to 50 minus 36. Right? So 50 minus 36 is going to be 14. Okay? And so you need to take the square root of 14. So it could be less, a little bit less than 4. So the closest answer will be A. Okay, so you see how you can simplify, because you have 2 times 5 is 10. 10 times 10 is 100. 0.36 times 100 is 36. So this exercise is also to see if you can do the computation in your head. Okay, so let's look at the last one. So this is the last one, maybe a little bit challenging if you didn't take calculus, but really you just need to know the definition. So if you have a work, okay, so if you have a constant force, the work will be the force times the displacement, right? So it means if you have a force here as a function of displacement from 0. Then if the force is constant here, this here, that will be your work. So the work is the area under the function f of x. So in that case, the force is going to change as a function of x. So the force equals 2x. So it means the force is something like this. It's a linear equation. You go from 0 to 4, and they want you to find the work done. So the work done will be this area here. So it's the 1/2, it's the triangle. The base is 4, and the height here is going to be 8. Okay, because it's 2 times 4 is 8. So here we have 8, which is 16 joules. Okay, so I don't think I will make new videos. I think I'm going to stop here.